Can't do any zoom in. I'm stuck with that. Okay, I'll just try to write bigger. I wrote way too small. Wrote way too small. So what this says over here is we've covered two types of functions so far. We've got exponential functions that look like a number raised to with variable power. And those functions are functions whose domain is the set of real numbers and whose range is a set of positive y values. All of our exponential functions pass through 0, 1. I wrote it backwards over here. 0, 1 is when it passes through. And they behave like things with properties of exponents. Anytime the power is 0, the value is 1. A negative exponent means to flip the base and then apply the positive power. When you multiply like bases, you add the exponents. When you raise a power to a power, you multiply exponents. And when you divide like bases, you can subtract the exponents. Then one of the important things is that these are one-to-one functions. And we use this property to solve exponential equations, that if we have two exponential functions equal to each other and the bases are the same, then the only way that can happen is if the two powers are the same. So this gives us one of our strategies for solving exponential equations. Try to write both sides in terms of the same power. Our other strategy is to use the inverse function called the logarithm. And I define the logarithm kind of in this two-part way. A logarithm is an exponent. For the logarithm base b of a number n is an exponent v if and only if b raised to the v power is equal to n. And so if we have an exponential equation that we can't write in terms of both sides in the same basis, maybe we want to know what v was, then we can just rewrite it in terms of its equivalent logarithmic form. Our goal, though, is to write it in terms of a common logarithm, and the two common logarithms are a log base 10 and the log base e. We write the log base 10 as just log. So when I write log of n, that means I'm looking for an exponent v if and only if I can write with this double-headed arrow, 10 to the v is n. The other common logarithm was a log base e. We write the log base e as the natural logarithm, abbreviated ln. So ln of a number n is an exponent v if and only if e to the power of v gives you n. And those are the two that we have on calculators, logarithm base 10 and logarithm base e. So if we happen to use this to find an exponent in terms of another logarithm, we had a change of base formula. And the change of base formula was let me write over here what's big. Change of base formula says that if you have a logarithm base b of some number, you can rewrite it in terms of either log base 10 or a natural logarithm. It's the ratio of the natural log of the n divided by the natural log of the b. If you want to use a log base 10, just replace that natural log with a log base 10. And it's easy to remember, the b is the subscript, it goes on the bottom, and then slide the n across the top. Then you can get this number by doing this on your calculator. This is calculus. We don't care about numbers. Logarithms are also one-to-one functions. In fact, they're the inverses of the exponential functions. But since logarithms are one-to-one, I can write the similar thing for logarithms. It says if you have a logarithm base b of something equal to a logarithm same base of something else, then the only way that that can happen is in the two articles of the logarithms are the same. Now, the fact that logarithms are inverses of the exponential functions give us these two graphs. They take all the ordered pairs on these graphs and reverse them, and then reflect the graphs about the line y is equal to x. So if you have a logarithm whose base is bigger than 1, then it passes through the ordered pair 1, 0, and has as the negative y-axis as a vertical asymptote. If the base is between 0 and 1, it still passes through the ordered pair 1, 0, but now the positive y-axis becomes the vertical asymptote, and then it's slowly decreasing forever. The domain of this function was all real numbers. That becomes the range of these. I have all real values of y. The range of the exponential functions were positive numbers. The domain of a log function is that the input has to be positive. So for any logarithm, x has to be strictly greater than 0. And then finally, the one-to-one relationship says that f of f inverse gives you back x, and f inverse of f of x gives you back x. So I have these two relationships. That if I have a base b here, and as its power, a logarithm base b of some input, I get the input back. These two undo each other. And in a similar manner, if I'm taking a logarithm base b, and in here I put an exponential function, same base, I get the original input back. So, like I said, we use the inverse property or this thing here to solve exponential equations. Let me solve a few exponential equations, and then I'll go and talk more about logarithms. So I'm going to erase those graphs. I need to keep this up here so I can point at it.
Why is the change of base formula log base 10 to natural log?
It can go to any logarithm. This is log base b. So whatever base is here, I can go to a natural logarithm, or I could go to a log base 10. Or I could go to a log of any other base. I could put log base a of n divided by log base a of m.
So it doesn't have to match like the original.
I just chose these because I think those are the easiest buttons on a calculator to find. And we're going to use natural logarithms almost exclusively through the rest of this course instead of a log base 10. So we're going to have a couple of strategies to solve exponential equations. First, try to write both sides in terms of powers of the same base. But if you can't do that, use a logarithm. Change it from its exponential form to its log form. So for example, suppose I wanted to solve for x. And in this first example, let's have 9 to the x minus 1 is equal to 27 to the x plus 2. So what I hope you see is that both 9 and 27 can be written as 3 to a power. And that's where I'll start. I'm going to replace 9 with 3 squared. and 27 with 3 cubed. Try to write them in terms of the same base. So I start by writing 9 is 3 squared. So I have 3 squared to the x minus 1. Right, 27 is 3 cubed to the x plus 2. Then we'll use the property of exponents to simplify this. Remember that when you raise a power to a power, you multiply exponents. So I can rewrite this as 3 to the 2x minus 2, and I can write this as 3 to the 3x plus 6. And now I have it the way I want it. 3 to a power is equal to 3 to a power, only if the two powers are equal to one another. So now I'm going to say that. That means that 2x minus 2 has to be equal to 3x plus 6. And so let's get the x's together by subtracting 2x from both sides. And then subtract 6 from both sides. That part okay for you? Okay, the second one will be of the other type. So if I had something like 2 to the x plus 3 is equal to 7. Now 7's a prime number, so I can't write that as 2 to a power. So I need to get that exponent down. So I'm going to change it from its exponential form here and put it backwards into its log form. So that says that the power will be the log base 2 of my number 7. That power is the log base 2 of the number 7. I'm going to show you an alternative to doing that shortly, but let's write it that way this time. So the log base 2 of the number 7 gives us the power. But now let's go ahead and write this in terms of the natural logarithm so it's more useful to us. This is the same as saying the natural log of 7 divided by the natural log of 2. And so then the last step is to subtract 3.
Sorry, on that other one, where did you get the -2?
This is the -2. Raise a power 2 power, you multiply exponents. So 2 times x, 2 times the -1. Anything else? Okay, now let me show you some properties of logarithms and look at log equations. Logarithms and exponent. So its properties of logarithms are going to mimic the properties of exponents in that when you multiply like bases, you add exponents. When you raise a power to a power, you multiply exponents. And when you divide like bases, you subtract exponents. We're going to have equivalent things that look like powers of properties of logarithms for those. So firstly, remember that a logarithm is the inverse of an exponential function. So the x's become the y's become the x's, which tells me that if I take a logarithm of 1, I'm going to get 0 because b to the 0 power gives us 1. Then a logarithm is an exponent. So if I have 2 logarithms, let's say this is an m, and this is an n, and I'm adding 2 logarithms of the same base together, that comes from having a product of 2 logarithms. This is analogous to if you multiply like bases, you add the exponents. When you multiply like bases, you add the exponents. When you raise a power to a power, you multiply. So logarithm base b of m to a power is going to be that power times the logarithm base b of m. When you raise a power to a power, you multiply your 2 exponents. And then finally, when you divide, 2 exponential functions of the same base, you subtract. The exponent. So the log of a fraction is the log of the top minus the log of the bottom. So notice we don't have an algebraic function. We don't distribute a log through a product. We can't say that's the log of m times the log of n. It's got its own mind. It's got its own property. The log of a product is the sum of 2 logarithms, right? The power here is on the article of the logarithm and not on the logarithm itself. So if the power is there, you can bring the power down as a multiplier. We're going to use this property a lot. The log of a fraction is the log of the top minus the log of the bottom. You can't just distribute a logarithm. And then the one-to-one function property that I wrote here a second ago, that if you have the log base b of m equal to the log base b of n, then the only way that can happen is that m is equal to n. We are going to use either this property to solve log equations or these kind of things in the definition of a logarithm to solve log equations. So solve log equations. We will either use the definition, the log base b of a number n is an exponent v if and only if b to the v is n. We'll either use that or the one-to-one property. So for example, suppose I have a logarithm base 3 of x minus 2. And I want to know what value of x makes that equal to the number 2. And so that looks like my first choice. I've got a logarithm one side and a number on the other. It looks like I can just go from here to here and figure out what x is. A log on one side and the non-log on the other. Just change it to exponential form. To do that, you say the number, the base raised to the right-hand side is equal to the article of the logarithm. 3 raised to the 2 power is equal to x minus 2. So I'm going to change to exponential form. And I'll just get the x by itself. 3 squared is 9. To solve for x, I add 2 to both sides. So x has to be 11. Okay. All right, so another example. Suppose I have the natural log of 2x minus 3, and it's equal to the natural log of 11, and I want to know what x is. So that's my other strategy. That one is this one. I've got a log on one side and the same logarithm on the other side. So the only ways that those two things can be equal is if the articles of the logarithms themselves are equal. Okay, so log equal to a log, same logarithm. So by the one-to-one property, these two are equal when 2x minus 3 is 11. So solve for x. We'll add 3, we'll divide by 2. Add 3 gives me a 14 over there. Divide by 2 gives me x is 7. Okay, here's your third one. Tell me what I need to do to solve this equation. 3 times the log of x is equal to 6. 3 times the log of x is equal to 6. Anybody got a plan? Go ahead.
Maybe not rule where it's exponential, but log b over log b and then n to n to the power b.
Yeah, take that upstairs if you want. You can do that. This thing here means it goes up here. Or this is just a multiplier. Another way we can look at it, we can divide both sides by 3. You can bring that up on the x, or you can divide both sides by 3. Okay, I'm gonna divide both sides by 3. The other way will work as well. I just get too big of a number eventually. I like to scale things down than to make them bigger. Now I have the same problem I had a second ago. A logarithm is equal to a number. When I don't have the base written, it's a log base 10. And now let's change it to exponential form. The base raised to the right-hand side is equal to the logarithm. So if you have a logarithm equal to a number, change it to exponential form. So 10 squared is equal to x. So there's our answer, x is 100. Now, we might have some mutation of these, and we've got to make the equation as easy as this. Either a log equal to a log, or a single log is equal to a number, and we can put several logs together by using these properties. So my next one's going to have several logarithms in it. I don't know if that's better or worse. So in my next one, I'm gonna have several logarithms. I've got log base 3 of 2x minus the log base 3 of x minus 3 is equal to 1. So eventually we want to get to a step where we have a single logarithm equal to a number. So I see the minus sign, and that tells me I can take those two separate logarithms and put them together as a single logarithm. So I'm using this middle property here, that I can write that as the log base 3 of 2x divided by x minus 3. Now change it to log form. 3 raised to the value over here is equal to the article of the logarithm. And solve for x. So 3 to the 1 is just 3. Let's multiply both sides by x minus 3 so I don't have a fraction anymore. And then I have 3x minus 9 is 2x. I'm going to move this over here. I'm going to move that over there. And so I have x is 9. All right, next example. Let's look at the log base 2 of x added to the log base 2 of x minus 3. And say that that's equal to the number 2. Which one do first?
Into the log base 2 of x times x minus.
All right, this property, take 2 separate logarithms that are added and write them as a single logarithm, multiply the articles of the logarithm together. If 2 logarithms are added, I can combine them by writing as the log of x times x minus 3. That's now the article of a single logarithm. So if you want to write that as x squared minus 3x in there, that's fine. All right, what's next? Okay, we're changing it to exponential form. 2 raised to the 2 is equal to 2x minus 3. I'm sorry, x squared minus 3x. And now I've got a quadratic equation. I'm going to try to solve it by factoring. We get a 0 on one side and then try to factor. So subtract 4 from both sides. Now I'm looking for factors of 4 opposite in sign that add to -3. You got any? -4 and 1. So it's x minus 4, x plus 1. Now set each factor equal to 0 to get 2 solutions. X is equal to 4 and x is equal to -1. One of those makes no sense. Go back up here and tell me which of those 2 numbers I have to throw away. -1. A logarithm is only defined when the article of the logarithm is larger than 0. If x is 4, both of those are larger than 0, but if x is -1, they're both negative. We can't take the log of a negative number. Can't have the log of anything negative. So even if we got 2 positive numbers, go back to the original equation and see if it makes any of the logarithms negative inside there. Have you used logarithms and exponential functions before? Pre-calculus maybe? What applications use exponential functions or logarithms? Exponential functions model things that grow. So exponential growth, things like population models or compound interest, things that grow as a percentage of the base. Logarithms are used to model things that grow but grow slowly. Logarithms are used in the Richter scale to describe earthquake magnitudes. Maybe you've seen the compound interest formula. If P dollars is invested at R% interest, compounded M times a year, then the amount in the account after T years is given by an exponential function that looks like this. The amount in the account is equal to the initial investment, and then it shows exponential growth. The base looks like 1 plus R divided by M to the M times T power. E is how much you stick in the bank. R is the stated annual interest rate. M is how many times interest is compounded. So typically interest is compounded monthly or quarterly or even daily, semi-annually. So if interest is computed monthly, then M is 12. Quarterly means M is 4. Daily means M is 365. T is in years. That's if interest is compounded, not simple interest. Compounded means interest is each compounding period figured on a new accumulated amount. So for interest, for example, if you invest $1,000 at, I don't know, 6% annual interest, compounded monthly, part A, how much is in the account in 4 years? Right? So I've given you P as 1,000. Interest rate we write as a decimal, so we write that as 0.06. Compounded monthly means that M is going to be 12 and T is going to be 4 right here. Let me write all that down. Use P is 1,000. R is 0.06. M is 12. T is 4. Let's put that all in there. That says that in 4 years, it will accumulate to 1,000. 1 plus 0.06 divided by 12 to the 12 times 4 power. So let me simplify a bit. So 6 over 12 is 0.5. So shouldn't this be 0.5 right there? Take 0.5 and then multiply by 0.1. I think that's right. Did I do that right? It's essentially what we got going on there. 6 over 12 times 1 over 100. So 6 over 12 is a half. And that moves the decimal 2 more places, so puts 2 zeros there. I did it right. How about that for mental math? That's kind of painful. Okay, then we'd need a calculator. So if you've got a calculator or your phones, let's see if we can figure out how to do this number. I have a phone on me. Scientific calculator, there we go. So let's say I'm gonna take 1,000 times 1.005 raised to the 48. So I'm getting $1,270 and about 49 cents. Were you able to do that? In my part B in this question, I want to know how long will it take for this amount that you initially invested, this $1,000, to double? How long until you have $2,000 in this account? So in this question, I still have that P is 1,000, R is 0.06, and M is 12. But now I'm asking you to find T, for which this accumulated amount is 2,000. And so when we fill that in, our equation will look like 2,000 is equal to 1,000, 1 plus 0.06 over 12 to the 12 times T power. And our job is to solve that equation for T. So we can do what we did before and write this as 1.005 to the 12 times T power. And I'm going to get this number out of the way so that I have a number equal to an exponential function. To get this number out of the way, let's divide both sides by 1,000. 2,000 divided by 1,000 is going to leave me with a 2. And now we have an exponential function equal to a number. So we can just convert it to log form. But I'm going to show you the alternative. We know that a logarithm, any base of something to a power, will bring the power down. So instead of converting this to a logarithm, say base 1.005, I don't want to mess with that. I'm just going to start with that equation and I'm going to take the natural log of both sides. So I'll have the natural log of 2 is equal to the natural log of 1.005. And that's raised to the 12t. Take the natural log of both sides. You do stuff to equations provided you do it to both sides. Taking logarithms works the same way. Now I'm going to use this log property that yanks that 12t down in front. Put the 12t in front of that logarithm. And now it's just a linear equation. I've got t multiplied with some numbers is equal to a number. To get the t by itself, just divide by those numbers that are surrounding it. Divide both sides by 12 times the natural log of 1.005. So I get the t by itself, and now I can go to the calculator and figure out this amount of time. So when you push it in the calculator, you get to tell the calculator where the denominator is. So let's see how I'm going to do this. I'm going to take my natural log of 2 on top. Whoops, I got to hit the 2 first. All right, natural log of 2 is about 0.69. Then I'm going to divide it by, now I'm going to put my parentheses. And I'm going to have 12 times, I want the natural log of 1.005. So how do I do that? Let me go backwards. How do I do that? Let me try that again. This calculator is not as obvious as I want it to be. Divided by parentheses. I'm going to do the log of 1.005 first. So I hit my 1.005 and my natural log button times 12, and then close the parentheses. Uh-oh, I don't think that was right. Well, I really screwed that up. I'm not getting it. We'll figure out the bottom then. The bottom is a little bit more than 0.05. And then I've got the natural log of 2 is 0.69314. So if I take that now and divide it by 0.05985, that makes more sense. So I'm getting T is about 11.58, a little bit more than 11.6 years, a little bit less than 11.6 years. Double. Is that what you got? Does that make you think of any questions you want to ask about logarithms, exponential functions, anything you encountered in 2.4? Yes, sir.
I was just confused when the bases are not the same, that it's like a log base n plus log base n. But if the bases of the logs are
But they're not equations, right? It's a calculate this.
yeah.
I think it is. Let me pull it up and then we'll do that. You got it? You got it up already?
Yeah.
I'll show you what to do there.
So with log base 2 of 4.
It's web work number 7. Log base 2 of 4.
Plus log base 3 of 1.
Because we can get these two numbers. Log base 2 of 4 is a power that goes on 2 to give me the 4. So 2 to what power is 4? So this number is equal to 2. Log base 3 of 1/9 is looking for a power that goes on 3 to give us 1/9. 3 to what power is 1/9? You called it, it's -2. So this is -2. So the answer is 0. So it's not an equation we're solving for, we're just evaluating logarithms. Right? This 2 is the power that goes on that 2 to give us 4. This -2 is the power that goes on 3 to give us 1/9. Yes, ma'am. Okay.
After that, it's equal to 3 minus 2x. X is less than.
Okay, what you have in here, f of x is equal to
3 minus 2x.
b minus 2x? Oh, I see what I'm saying, we're doing a piecewise function. Okay,
And then -6 over x minus 3. And x is greater than or equal to
and we're trying to find out what value of b makes this continuous. I think that's true. For what b is this particular function continuous? Okay, what B is continuous for all x. So what we need is, well, this is just a linear function. And this is not going to be defined when x itself is b. So we got to be careful to figure out what b is here. But one of the things we need is this piece of the graph to hook up with that piece of the graph. And the hookup point occurs when x is -1. So we need the two pieces to hook up. We write that as one-sided limits. We need the limit as x goes to -1 from the left to equal the limit as x goes to -1 from the right. But when I'm coming in from the left, I'm using this, b minus 2x, to equal the limit as x goes to -1 from the right. When we're coming in from the right, it's this other piece, -6 over x minus b. Now, provided b is not -1, then we can just set these two equal to one another when x is -1. So b won't be -1 and I'm here. Well, we'll find out. Let's just set them equal to one another, but put -1 in for x. Let's see if we can solve that for b. So I get b plus 2 when I do this multiplication. And over here I have -6 over -1 minus b. What would you like to do next to try to solve that for b? Multiply by the denominator. So we'll multiply that up here. So I'm going to have -1 minus b times b plus 2 is equal to -6. Now let's multiply that and see if we get anything nice. -1 times b gives me minus b. -1 times 2 gives me -2. -b times b gives me -b squared. And then -b times 2 gives me -2b. And so I have -b squared minus 3b minus 2 is equal to -6. Everything's negative. Let's multiply by -1 and get rid of all those minus signs. B squared plus 3b plus 2 is 6. Just multiply by -1. And now let's get a 0 on one side because we're going to try to factor. So I'm going to subtract 6 from both sides. Then we're looking for factors of 4, opposite in sign, that add to +3. Got them? What are they? +4, -1. Now set each factor equal to 0, and you get b as -4, and here you get b as 1. So we have two values, and then you enter them some way with a comma or something like that. How do they ask you to enter them? The greatest value of b would be b as an absolute value. So then you put that one.
And then if you have to draw it, it'll ask you to look at it.
They ask you to draw a graph. Okay, well, if b, we have to have two different graphs because you get two different functions. So for example, if b is equal to 1, we graph f of x equal to 1 minus 2x for x less than -1, and -6 over x minus 1 if x is greater than or equal to 1. So do you recognize that first part as being a line? It'll be just a line segment because we have to end it when x is -1. Put a -1 in there for x, and that line segment ends at that ordered pair -1, +3. So let's plot the point -1, +3. And that's a strict inequality, so we put a circle there. And then let's just plot one more point here. If x is -2, I get a +4 + 1 is 5. And then it's a line segment, so I just do something like that. The next one is going to come and fill up that hole, because if x is 1, oops, -1. If x is -1 here, this becomes -2. -6 divided by -2 is 3. So now that fills that hole up. That's what we needed to make it continuous. That's not a straight line. In fact, that's something that's not defined when x is 1. And let's see, if x is 0, if x is 0, y is going to be a +6. And so it does something like this. It's going to turn up here. Never cross that line. And then maybe if x is 2, 2 - 1 is 1, then I'm down here at -6. And so it's going to do something like this. So it's really not going to be continuous for all x, right? There's a discontinuity here at 1. I wonder if they ignore that. Does it just want it to be continuous that x is -1? Maybe that's the way it's stated. Just wants to know what makes it continuous that x is -1. Good. Then the other graph will look something just like that, shifted over. Again, Owen?
To the log base 2, 3 minus log base 2, 5.
Those both logarithms are up in the exponent. Okay, we can do that. So first, let's simplify the difference between two logarithms. How would you do that? You can make two logarithms subtracted into one logarithm by doing what? Dividing. So I can make this all into a log base 2 of 3/5. So I have 2 to the log base 2 of 3/5. Now, what happens if the exponent has the same base as the exponential function? They cancel each other out, right? And so we come back with the original input of 3/5. That's the inverse property.
Would it be the same as like the 2 is only from the log base 2 to 3?
What do you mean?
Like
If this were gone?
no, like, because mine is 2 log base 2 to 3 minus log base 2 to 5. Like it's not all multiplied by 2. Like the parentheses aren't on the.
But I think that's all meant to be in the exponent. I think. I put the parentheses to emphasize. Yeah, see, all that's up in the exponent. And then-
Oh, I didn't even.
yeah. Anything else?
I got lost on this one because this was. Right.
Right, so this was just squared, right? 2 squared is 4, so this exponent is 2. 3 to the -2 is 1/3 squared, so that's 1/9. So that was just a -2.
But if those aren't the same thing, I don't know. Since it's 2 to-
Those aren't, this isn't the same as 2 to the 2 squared. Let me do that one another way. Let me write it this way. How about, let's do this. Going back to that other web work problem. Was this a minus or a plus? Plus. Okay, this time I'm gonna work inside the parentheses. I'm gonna write that 4.
Sorry.
I'm sorry,
It was
it's plus?
plus.
I'm gonna write that 4 as 2 squared, and I'm gonna write that 1/9 as 3 to the -2. So that's another way to look at this problem. Then we use the inverse property. Since this is a base 2 and that's a base 2, then these two cancel each other and we're left with this 2.
Okay.
And these two cancel and we're left with that -2. So that's yet another way to look at that problem. Anybody else? You got one?
Log x equals 5. Or no. Yeah. Log x equals.
We want to know what x is?
Yeah.
It's all for x. What number is this one?
Is 11.
Number 11. So we've got a logarithm equal to a number. Our plan is to change it to exponential form. What's the base when we don't write it? 10. So you're imagining a 10 down here. And when you change it to exponential form, it says the base raised to the right-hand side is equal to the article of the logarithm. So I change it to exponential form to get 10 raised to the 5.1 is equal to x. And there's our x, 10 to the 5.1. And you can put it just like that in Webwork, 10 to the 5.1.
Would you also do natural x squared equals 9? And also for those
Both of the x's. So let's again, we've got a logarithm equal to a number. So let's change it to exponential form. What's the base when we have a natural log? E. So this says that the x squared is e to the 9th. And you solve that by taking square roots of both sides. So there are your two answers, the positive square root of e to the 9th and the negative square root of e to the 9th. Let me see how you typed it in. Did the smaller one first. So it says that or some Anything else?
One
Okay, great.
e raised to the power 4 plus 4 equals 2.
All right. So this is kind of backwards. This is an exponential function equal to a number. And you either write them both in terms of the same base or you change it to log form. What's the log form of this? What's the logarithm base e called? Natural log. So this says the exponent is the natural log of this number. Right? We have the relationship with the natural log of anything is a number, means that e to that number is the anything. Those two are the same expression. So we're taking it from here and putting it back there. Or you could look at it this way. Remember we solved that one equation by taking the natural log of both sides? We can do that here. Take the natural log of e to the 4x plus 4 equal to the natural log of 2. But then you've got to recognize that these two are inverses. A natural logarithm is a base e, and this is a exponential function base e. So these two cancel each other out and just give us the exponent back. And now we can solve for x. Subtract 4, then divide by that other 4. And there's our x. So let me write that down separately. Maybe it's easier to remember that way. This is the inverse property, that the log base b of b to anything is that anything, and b to the log base b of anything is that anything. But also, if I do this in terms of natural logarithms, the natural log of e to any power is that power. And e to the natural log of anything gives you back that anything. Those are the inverse relationships. For log base 10, it says 10 to the log of anything is anything. And the log base 10 of 10 to a power is that power. That's all the inverse relationships. So if you want to bring an exponent down, you can convert it to exponential form, or you could take the log of both sides. And anytime I say take the log of both sides, I'm going to use a natural logarithm. You can use whatever one you want. It's America. I'm going to use a natural logarithm. Anything else? Need to stand up and stretch and take a 5-minute break here before I bust into the next section. We'll take a restroom break. Stretch your legs. Give me 5 minutes or so, and I'll try to end class about 5 minutes early. I'll try. I never do. I always keep you 5 minutes late, don't I? But I don't charge you extra for that extra 5 minutes of instruction. Any questions from the home front? Anything you want me to work, Riley?
No,
Okay,
I'm all good.
that's what I heard. All righty. We're going to start section 3.1 in about 5 minutes. Look at our schedule here. How are we doing schedule wise? Today is the 3rd. We're doing pretty well. It's really not taking a break if you don't even get up and stretch. There you go. What did 0 say to 8?
Something about it being twisted or something.
Nice belt. Bad, huh? Very bad. I heard that on the radio again. Again, that was a dad joke. I'm surprised you guys are Super Bowl fans. It's great. I had Mahomes in class 2000 and I think 2005 maybe. Not that long ago. It was in my business calculus class. It was a 9:30 class on Tuesday, Thursdays. And so that was his first class of the day. They had football workouts in the morning. And so he'd do his football workouts and then they'd have their little breakfast with the team. And every day he'd come to class with a big old handful of Starburst candies. We had tables and he sat on the right-hand side of the back table and he'd put his Starburst candies down and start eating them and then make a stack of papers. When they were all gone, he'd put his head down and go to sleep. And all I thought was, how could you sleep after you ate that much sugar?
Who's your NFL team?
Unfortunately, it's the Cowboys, but I have been following Pat and Cliff. So I like the Cardinals and I like the Chiefs. 'Cause they're better than the Cowboys. All right, let's go on to the calculus part. In chapter 3, we're going to learn about something called the derivative. Any of you had calculus before? So you've done derivatives and you know that there are nice, cute little rules for finding derivatives. But we're first going to look at the historical concept of what a derivative means and how it came about. We're looking at going from an average of something to what is the instant of that something. So when we talk about a curve, I'm going to do an introduction to the derivative. So consider a curve that looks like y is equal to f of x, just some random function. If this function were a straight line, I would know how steep it was by its equation, because the steepness of a line is given by its slope. If it's a function that is a polynomial looking thing like this, the steepness depends on the point. This point might have a steepness that looks like a negative number. I'm going down. If I walk in here, I'm going down, pretty steep. Then it kind of flattens out for a bit, and then I start walking up. So the steepness changes in sign and by amount. The amount of steepness of a curve will be given by something called its tangent line. The tangent line to a point on a curve. So for instance, we consider this point P right here and say it's at the ordered pair X, Y. The tangent line to that point will be this red line right here that touches the curve at that point, just in a local interval around that point. And it touches only at that one point. And whatever the slope of that tangent line is, will be the slope of that function at that point. The tangent line to point P has the slope of the graph of P, or the graph of F, at that point P. Our job is to find the equation of that tangent line. We've written equations of lines. We need two things, a couple of points, so that we can do y2 minus y1 divided by x2 minus x1, and that gives us m. Well, on this particular line, I only know one point. So here's what we do. We find a point near that one, say over here. Let me just make it way over here for now. Here's where we have x. Let's move over from that x by an amount. And I'm going to say I'm going to move by h units. H is going to represent some decimal. So if that's x is 2, that might be x is 2.1. Now that I have 2 points, let's call that point Q. Now I have 2 points, I can find the slope of the line that connects those 2 points. Nope, not with that marker. Purple. If I have 2 points, I can find the slope of the line through 2 points. The line that connects 2 distinct points on a curve will be called a secant line. So a tangent just touches 1 point, a secant connects any 2 points. Okay, so we can write the equation, or we can find the slope. Let's just find the slope. I don't care about writing the equation just yet. We can find the slope of the secant line through a nearby point. We find the slope of that secant line and say, well, that's going to be roughly equal to the slope of that tangent line. So I need the ordered pair here. The x is x plus h. To get the y value, I have to take that and plug it into the formula to figure out what the y coordinate is there. So for now, I'm just going to call it f at x plus h. And then I'm going to use my slope formula, change in y over change in x, to get the slope of the secant line. So let me write that as the slope of line PQ. It's the change in y over the change in x. And so for our notation, I'm going to use this as my x2, y2. This is my x1, y1. And so we'd have y2 minus y1, but instead of calling that y, I'm going to call this f of x. So that I can keep the same notation. So f of x plus h, y2 minus y1 divided by x2 minus x1. And of course, these two x's add each other out. Then we get something like this. And my claim is that that slope of that line is roughly equal to the slope of that red line. You look at it and they don't look very equal at all. Right? This one looks like it's a smaller number in my picture than that one. So my problem is I picked this point too far away from point P. So I'm going to move closer. Pick a smaller number, move that point closer. Let's call this one Q1. Squeeze this point closer here by picking a smaller number for H, and then find the same calculation for these 2 points. Now that line looks like it has a slope closer to the slope of the red line, but still not exact. So do it again. Pick a point Q2 closer to point P. And that means I'm making H smaller. Find the slope of that line. And I do that an infinite number of times. I keep squeezing point Q closer and closer and closer and closer to point P until you can't even see the difference between point P and Q, till they're essentially the same point. And I don't do this calculation-wise. I do that by making this point slide toward this one, by picking H smaller and smaller and smaller. We do that with a limit, right? So as H gets smaller and smaller, then point Q gets closer to point P. And that secant line becomes the tangent line. And this expression here, which is the slope of the secant line, will give us the slope of the tangent line, provided we take the limit as this number h approaches 0. So we say the slope of the tangent line is equal to the limit as h goes to 0 of f of x plus h minus f of x divided by h. So it's just the idea that we take distinct points, find their slope with this thing called the difference quotient, which is just y2 minus y1 over x2 minus x1. Pick two distinct points and then fake out that second point. You say you're really not a distinct point because we're going to take h to 0 and make our 2 points indistinguishable. So we find the slope of the tangent line by taking that h to 0. We had an interval became an instant with a limit. So how about we try an example? Let's let f of x be 4 minus x squared. You know what the graph of that looks like? Okay, upside down parabola. Vertex at 0, 4, crosses the x-axis when x is 2 and negative 2. Let's look at the point 1, 3. If you were to draw a tangent line to the graph at that point, would your tangent line have a positive slope or a negative slope? It would have a negative slope. And it would have a negative slope that's kind of steep, right? The tangent line there is kind of steep. What I want you to do is pick our point Q to be right here at 1-ish. Q. So it's going to be like 1 plus h. And then I need to find out what f is at 1 plus h. I want you to find the slope of the line through PQ. And then let's put a limit on it. And then we'll find the slope of the tangent line. So write an expression that gives the slope of the secant line that I've labeled PQ. Just for this example. So here's what you're thinking. Here's the slope of the secant line. y2 minus y1 divided by x2 minus x1. So here's my y2. Well, not quite. I haven't figured it out yet. What does that look like for our particular function? What does f of 1 plus h look like? How do I find that? I want to know what my y2 looks like for this particular function. What do I do to find f of something? What if I wanted f of 2? Plug a 2 in. So if I want f of 1 plus h, I plug in 1 plus h. So let's rewrite that with the 1 plus h. Okay, so that's my y2. So I have f of 1 plus h minus f of 1. Then I take 1 plus h and I subtract 1. So the slope of line PQ is f of 1 plus h minus f of 1, y2 minus y1 divided by x2 minus x1. Change in y, look at the change in x. So I have both of these numbers now. This looks like that. Oops, that should be squared, right? F of 1 I already found. 4 minus 1 squared is 3. And then this down here simplifies to h. Okay, now, next, let's find the slope of the tangent line to f at point P. And that's what we're going to do next. We take that very expression that we have right there, and we take the limit of it as h goes to 0. Well, what happens if you plug 0 in for h right now? You get 0 divided by 0, right? Which is our clue to do more. So we'll do what it tells us to do. Let's take 1 plus h and square it. So 1 plus h all squared is going to give us 3 terms, right? Tell me what the 3 terms are. Apply that out and simplify it, and what do you get? Don't subtract yet. Just do this part for me.
1 plus 2.
There you go. I get paid by the number of steps I do, so I just make 15 cents right there. So in the next step, I'm going to distribute the minus sign. Take the parentheses away and distribute the minus sign. That makes everything in here opposite in sign. And now I'm going to collect like terms. The constant terms, I've got 4 minus 1 is 3, minus 3 is 0. That's not a 3 on the bottom, that's an h. Good golly. So I'm left with minus 2h minus h squared divided by h. So I got that common factor of h that I can pull out now. And that leaves me minus 2 minus h in here. And then I can cancel it. And as soon as you cancel it, now you can take the limit by substituting 0 in for h. And we get the slope of the tangent line to be the number -2. And that's what you told me. We should get a slope that's a negative number, and it's pretty steep right there. I bet by symmetry, that's the slope of the point over here. at x is -1, but at x is -1, I bet it's a +2. What do you think the slope of the tangent line is at the vertex up here? Should be 0. Looks like the tangent line should be horizontal right there. Let's do that. Let's compute the slope of the tangent line at x is 0. So let's do this calculation again, but this time we're using x is 0. Okay, so the next problem, find the slope of the tangent line to this graph at x is 0. So at x is 0, y is 4. And so this time we pick our nearby point to look like 0 plus h, f of 0 plus h. So we use our nearby point 0 plus h, f at 0 plus h, which is just the same as h, f of h. And f of h is just 4 minus h squared. Right? So if this is my x2, y2, and this is my x1, y1, then the slope is change in y over the change in x. Change in y over change in x. You can simplify that by canceling the 4's. And then we change it to a tangent line by taking the limit as h goes to 0 of that reduced expression, which can now reduce one more step. Cancel the h. And then plug 0 in for h. So just like the picture tells us, the slope is going to be 0. And now if I took that same function and asked you, say, for the slope at x is equal to -2, then you got to start over. -2 plus h is the nearby point, f of -2 plus h is its y value, and do the same calculation. Or we could have just done it in general at the beginning, and then substitute in different values for x at the end. So let's compute a formula for the general slope to this graph at any x. So let me rub some of this stuff off. So instead, let's use the fact that the slope of the tangent line is equal to the limit as h goes to 0 of f of x plus h minus f of x over h to compute the slope at any x to this very same function. So instead of sticking numbers in, we're just going to use the algebraic expression. Simplify the algebraic expression and then take the limit. Are you ready? First thing is, label it. We find this guy. So we go to that equation, replace x by x plus h. So you have 4 minus x plus h all squared. That's this guy. Then you subtract off the formula as you see it, 4 minus x squared. I'm going to put it in here. And then you divide by h. Right? Everything we did with numbers, we can do it to the variable h. So I need you to do the squaring for me. I need to expand this. And I need to put it behind this minus sign. Who wants to take a shot at it? What is x plus h all squared? Got the x squared. What's the middle term going to be? I'm going to have an xh done twice, right? And then the last term is just going to be an h squared. Agree? Then back here, I've got this. I'm going to distribute the minus sign here. And then I'm going to divide by h. Got a lot of simplifying to do. I got to distribute the minus sign through the parentheses. If you want at the same time to get rid of the 4s, you can. I got a +4 in the front and a -4 somewhere down the line there. So this one subtracts that one out. And now I'm going to distribute the minus sign. And then you see something else we can get rid of. Got minus x squared in front, plus x squared in the back. You should always end up with a step where the non-h terms add each other out. And everything else has an h in it, which will allow us to cancel this h from the bottom. So I'm going to do the factoring step, factor out that common factor of h. Then I get a -2x minus h up here. Cancel the h. And then we take the limit with what's left. What's left was -2x minus h. And my limit takes that variable h to 0. And we're left with -2x. It says anywhere on this graph, if you want to know its slope, take the x coordinate and multiply it by -2. So that's why when we found the slope here when x was 1, we got -2. The slope when x was 0 was -2 times 0. So what's the slope down here at this point? 4, right? Anywhere on here I can find the slope now just by doing it in general. This general calculation, finding the slope of the tangent line, is called the derivative of that function at any value of x. So we write the derivative as the difference quotient. Limit as h goes to 0, f of x plus h minus f of x all over h is the derivative. Well, there are several ways to denote the derivative. We denote the derivative by the name of the function, and then we put a prime here. And that's how you read it, f prime at x. Another way to denote the derivative, we have that y is equal to f of x. So sometimes you'll see it denoted dy dx. To show you the relationship between the instantaneous rate of change and the average rate of change. When I first wrote this expression as the change in y over the change in x, I used that triangle, delta y over delta x. You see the delta, that's the average. When the delta becomes the d, That's after we take the limit, and it becomes the derivative. And so in this picture, we would denote that f prime at x is negative 2x. We saw that f prime at 0 was 0. F prime at 1 was negative 2. F prime at negative 2 was a positive 4. So we're going to compute derivatives of easier looking functions using this. Then in section 2 of this chapter, we're going to develop some general rules so we don't always have to go back to this derivative. How's that sound to you? Right now, the derivative describes the slope of the tangent line. We're also going to use the derivative to give any instantaneous rate of change. So we'll pick it up from there on Friday. Today is Wednesday. Hump day. Okay, make it to your chemistry class in time. What are you gonna do in chemistry lab today? Nothing fun? Well, the first lab you learn how to keep your goggles on.
Remembering a textbook, it's really fun.
Yeah.
We still have to do it.
Take advantage of it when it's easy, because it ain't gonna be easy all semester. All right, Riley, you good? I'm gonna cut you off.